Oh, good evening, good morning, whatever time of day it is, I'm not sure anymore. Welcome to a little video clip on section 11.6 in your textbook, Osmotic Pressure and Osmosis. It's an interesting property of solutions that we can measure, and very important to biological systems. First of all, a semi-permeable membrane can be man-made, or there are many examples in nature. Almost every cell wall or cell membrane has some kind of semi-permeable nature to it, where water, especially usually, can travel through to and fro across the membrane in an effort to achieve something. I'll say what it is in a second. But the solutes and even many small ions cannot travel through the membrane, which leads to Mother Nature often trying to water things down to even things out. If a concentrated solution is on one side of the membrane and a less concentrated or pure water solution is on the other, or pure water on the other side of the membrane, then water will flow, or the solvent will flow from high concentration to low concentration in an attempt to water down or even out the concentrations. It's just a really weird property. I guess nature likes to even things out, achieve some kind of equilibrium balance. An example of this is in medicine. Another extension of this, the dialysis system, where if someone has poorly functioning kidneys, to filter their blood, we can actually remove their blood, pass it through a dialysis unit, which filters out a lot of the wastes, particulates that the kidneys aren't able to filter. In this case, humans have built the dialysis system so that small ions and solutes may actually be able to pass through along with the water, but not the larger molecules, nasty proteins and waste junk. Let's look at some pictures. Osmotic pressure. Here's some pure water out here. Here's a solution inside this ball, this glass sphere. Down at the bottom is a semi-permeable membrane where the water can flow in and out of. But since it's pure out here and a solution inside, the water will travel up through the membrane into the container, trying to water that down. And what was the normal height of the solution inside equal to this height of the solvent outside, over time you see this level goes down and this level goes way up. And the height of this liquid, along with its density, can be used to measure in a kind of a physics sense, a physics type calculation, the pressure, the force of this water trying to water that down. It stops over time. It does not continue to rise, depending on the concentration of this and the temperatures. Here's a cartoon of that. Although this seems backwards, the solvent here was right here, and the solution, the solute-solvent mixtures inside there. Anyways, the water would flow through the pores like that, and these particles could not pass through going to the other side. Another example picture, kind of like a U-tube here. There's a semi-permeable membrane in here. We put some pure solvent, probably water over here, and a solution over here. Originally they're at the same height, but like say in here somewhere in the middle, but the water, the solvent, tries to go passing through the membrane into the solution, watering it down, resulting in this level growing higher and this level smaller. And the difference, let's see, that would be, I don't know, pi r squared h. That would give me the volume, and you could use the density to find the weight of the thing and hence the pressure. That's physics. Here's another example. Some red dye in a tube with a dialysis or semi-permeable membrane down here, and we put it in some pure solvent. Initially this level and this level are the same, but over time the red dye gets watered down as this water, the pure solvent, goes up into the bag, and the membrane, into the solution, and waters that down. You can Google all kinds of images of dialysis. Here's a pretty simple, let's keep it straightforward equation. A capital pi from the Greek alphabet, it stands for osmotic pressure. Molarity, the more concentrated the solution is, the more pressure it can build. And temperature, directly proportional to the Kelvin temperature. And here's the old gas constant we've come to know and Fear. What's the osmotic pressure associated with a 0.021 molar sugar water solution? 25 degrees. I don't know. Let's do a little calculation. 0.021 molar. R is the gas constant. Doesn't change. Kelvin temperature. Add 273 to the Celsius temperature. This liter cancels this liter. This mole cancels this mole. This Kelvin cancels this Kelvin. And you're left with atmospheres as your final unit. Couple of more examples. Have you heard of reverse osmosis filtration systems? Osmosis would usually have the pure water traveling from the pure side through the membrane to the solution side. But in reverse osmosis, we use very high pressure to push the dirty water this way, and the dirtiness of the ions, the contaminants, the junk gets all trapped up in the membrane or can't make it through, but the water does make it through if the pressure is great enough. Again, I put the seawater, the impure water, whatever you're trying to purify, in this side and push it very, very hard. Lots of pressure. I don't know. I'd have to look up. I'm sure it depends on what unit you're using, but what device you're using. But the solute particles get trapped over here, but the pure water makes it over into the right-hand side. It's a purification system. Or, just for comparison, this is osmosis, where I flow from the solvent to the solution, and this rises up higher. Oh, I've heard that Catalina Island off the coast of Southern California uses reverse osmosis building systems to filter the seawater and provide drinking water for the island residents. I put the seawater in here under a lot of pressure, push it through the membrane, and the water emerges over here clean and pure, and the extra salts are just dumped back into the ocean. Hey, thanks for